Hi all, and welcome to the Medical AI Lab group session. Today I'm delighted that we have Kyle Alford presenting to us on DoubleMatch, which is improving semi-supervised learning with self-supervision. Without further ado, Kyle, take it away.
Yes, thank you, Pranav. Really excited to present DoubleMatch. I think it's going to be pretty interesting to see some of the results that they came up with and some of the formulations and the framework that they actually created. So without further waiting, we can go ahead and get started. So just to quickly give a presentation outline, I'll go over a quick, really brief background over some of the challenges that DoubleMatch addresses and some of the similar methods that they're building upon, because it really makes more sense when it's put into context with the previous work, previous state of the art. And then I'll go into the specific methods like the loss functions that they're adding and the specific algorithm that they're using. And then towards the end, I'll go into the experiments that they used and some of the results that they actually ended up creating. And then I'll leave time at the end for Q&A in case there are any questions. There we go. Right, so semi-supervised learning, really briefly, in situations where there aren't enough labels just due to complex task in labeling, or it may be expensive to actually label the data, using unlabeled data is far easier in those situations. It's just easier to not label the data and just use that. And so semi-supervised learning is a set of methods that utilizes mostly unlabeled data and then either a similar amount or even more usually less labeled data to achieve some task. And in this paper, the authors really emphasize these 2 points in improving the semi-supervised learning performance in terms of consistency regularization, which can be thought of as basically encouraging consistent predictions on different versions of the same sample, sorry. So for example, in computer vision, this would be different augmentations, trying to maximize the similarities between different augmentations of the same image, and pseudo labeling, which is using confident model predictions on unlabeled data as the training labels. And so throughout the presentation, just want to keep these two different terms in mind because they come up rather frequently. Yeah, so the previous state of the art that DoubleMatch is building on is called FixMatch. It's out of a team from Google AI, I believe. And basically, the team here, DoubleMatch, they're postulating that FixMatch leaves out difficult examples, and I'll go into exactly what their framework was, but it uses the same framework of consistency regularization in the form of augmentating the images and then pseudo labeling, and it was able to achieve around 95% on CIFAR 10. And as I said before, the problem the team is trying to address is that the loss function used in FixMatch only regularizes confident data that produces confident model predictions. So for some of the more difficult tasks, it causes some data samples and data slices to be ignored fully. And so DoubleMatch is trying to address that by encapsulating the entirety of the unlabeled data set rather than the easier task. So really quickly, this is just the framework for FixMatch. And this is very important because this is, like I said, what DoubleMatch builds off of. So their framework will look very similar. So for the unlabeled example, it's basically taking the image, splitting it into a weakly augmented and then strongly augmented image, pushing those both through a model. And I'll go into more details about the augmentation in the model later, but it pushes those through into the model. And then the weakly augmented branch above here is treated as almost the teacher in, for example, a teacher-student network. And so this is what's being used. Those outputs, that prediction is being used as the pseudo label. So here in the red, it produces the probability distribution for each classification bucket. And then uses a hyperparameter, this threshold. And so it only uses this example if one of the classes are above that threshold. As you see here, one of these are above. And so it'll basically one hot encode that and use that as the pseudo label. And so the problem here is if it's a more difficult task where this probability distribution would be more uniform and none of the buckets actually pass that threshold, it's essentially left out. And I'll go into details as to how that actually happens mathematically later on. But the general idea is using this as the teacher to pseudo label for the strongly augmented branch and using a cross entropy across that. Right. And so to actually introduce double match, it's extending FixMatch, the previous state of the art, by adding self-supervised loss. So the goal is not to predict just the classes as was done in FixMatch, but also to learn the representations that can also be used for a downstream task, which is the classification task. So what I just showed was strictly what they call in the paper the label space. So evaluating the model based purely off of the predicted class distributions, also called in the paper the pseudo label loss. But FixMatch doesn't deal at all with the representation space, the feature space, which evaluates the model based on the similarity of the predicted representations. So this feature space is what the double match team is essentially adding. And so this is the framework for double match. And I sort of blacked out this middle part, so just pretend that's not there. But ignoring that middle part, this is essentially the same thing as the same framework as the FixMatch that I showed earlier, taking the unlabeled image, augmenting it, pushing it through, getting the pseudo label, and then the class distributions for the strongly augmented image, and then comparing it with cross entropy. And so what they're adding here is taking that strongly augmented image, taking those representations, and also I'll define these terms right here. F is just the neural network leaving out the projection head, and then these G's are the linear projection heads. So up to this point, pushed through F, Z and V, these are just the representations. So taking these representations and pushing them through into a cosine similarity function, that's what they're adding to produce this self-supervised loss, which is what they're claiming is increasing the performance generally, both in training time, decreasing the training time, and increasing the performance in terms of accuracy. So now I'll go into the math of everything, and just bear with me because there's so many symbols. But again, going strictly only for FixMatch, the FixMatch loss consists of the supervised loss, which is just taking the images and their label, pushing it through a cross entropy here, with B being the batch size, and this was just being the cross entropy function. And then for the unlabeled data, they use the pseudo label loss, which is what I was showing earlier, where this tau hyperparameter is that threshold, that dashed line. And so the maximum value probability within that distribution is above the threshold, this indicator function will evaluate to 1, and the cross entropy will be used. And if not, if it's less than that, this value is 0. And so then everything else is essentially tossed out. And just to define more terms, W here is the weakly augmented, that top branch distribution. And then Q here is the strongly augmented distribution. So calculating the cross entropy between these two. And so for adding double match, what they're adding is the self-supervised loss, which I spoke about earlier, which is basically the negative cosine function between the representations now, as opposed to the final probability distributions. And so VI, again, these are the representations from the strongly augmented images, and then ZI are from the weakly augmented images. These are representations. And then pushing this through the strongly augmented through projection head, that's what H is, and essentially calculating this negative cosine loss. So that's what they're adding that essentially boosts the performance in their experiments. And so the overall loss is just the sum of all of these different losses, the three losses that I just went over, the supervised, pseudo label, and the self-supervised. And then they also add this weight hyperparameter. So just to note that if you push the value for this weight to be 0, this is essentially just FixMatch, the sum of these two losses. And just really quickly, this is the overall algorithm, the DoubleMatch algorithm. I won't go too deep into it because it's basically just, it would be re-explaining what I've already explained, but you have the supervised loss being calculated for the cross entropy. And then down here, you have the unlabeled data where it's segmented into the self-supervised loss and the pseudo-labeled loss. And let's see. Also, the stop grad function here is just because the weakly augmented branch in the network is treated as the teacher network. That's just basically for back propagation. It's pausing, it's stopping that gradient from being propagated through. So only the student network is actually learning. And then before I go into the results, just really quickly, here are quick training specs for how they trained the networks. And so for the weak augmentation, they just used horizontal flips with a probability of 0.5. And they also used random translations with a max of moving 0.125 or 12.5% of the maximum height of the image. They used SGD with Nesterov momentum. With the cosine learning rate scheme, they used a batch size of 64, and they used a wide ResNet. And then for here, they varied for the experimentations. They varied using both a wider ResNet and then also a larger representation dimension for the representations used in the self-supervised loss. Yeah, so to get into the results, what they found was that DoubleMatch performed well for harder classification tasks. So they list out a few of the similar works and competing works, MixMatch, FixMatch, what I spoke about before, previous state of the art, and then UDA and MixMatch being a similar paper from Google Research again. And just looking at the different data sets that they used for CFAR 10, it actually doesn't achieve. Oh, and then also really quickly, these values are the error rates. So the lower value being the better rate. And so for CFAR 10, DoubleMatch doesn't actually achieve state-of-the-art low error rates. It's actually still DPSSL and DASH for different amounts of the labels for each data set. You don't actually see the improvement in performance until you increase to CFAR 100, where it achieves the lowest, out of all of these, the lowest error rate for all of the different label amounts. And so they were saying basically that this could be due to the self-supervised loss for the unlabeled data. For an easier classification task like CFAR 10, it's essentially less important. Whereas for a harder classification task, for 100 different classification classes, it's actually more difficult. And so actually learning that self-supervised representation task is going to add a larger performance boost. And similarly for SVHN, just like CFAR 10, didn't really achieve state-of-the-art error rates. Why is this not? Oh, and then also one more thing, the difference between these two, the DoubleMatch here, last 20, is just taking the median error rate across the last 20 training evaluation, or the last 20 steps, whereas this is just the minimum throughout the entire training process. And yeah, this is just the same image, just zooming in on CFAR 100 to see the lower error rates, which is essentially what I was talking about before. And then they also stated that it decreases the training time. And so this is comparing both DoubleMatch and then FixMatch. As you can see in the red, FixMatch takes more training steps to achieve their baseline accuracy, whereas for DoubleMatch, it takes less training steps to achieve a higher accuracy for CFAR 10 and then also for STL 10 to achieve a similar accuracy. And then lastly, they performed a few ablation studies. And so just to justify the choices they used for the self-supervised loss and the function they used for the pseudo label loss. So here for the self-supervised loss, they landed on a negative cosine function, just because that ended up resulting in the lowest error rate, whereas they compared it with mean squared error loss, and as well as a softmax loss here, which I put here, and also varying this lambda hyperparameter. There we go. And then for the pseudo label loss, they studied the reduction in test accuracy on CFAR 100 by just completely removing the pseudo label loss and looking at the test accuracy for different amounts of labeled training data. And so for the larger amounts of labeled data, they saw taking out fully the pseudo label loss resulted in only a 0.39 reduction in accuracy, whereas when there are less labels, for example, 400, there's a lower accuracy, so a higher reduction in accuracy. And so the team basically stated that their future steps were, for DoubleMatch, they focused on improving the consistency regularization of steps through the self-supervised loss. But in similar works, for example, from the first table and comparing the similar works, these worked on improving the pseudo label loss. And so looking at things like FlexMatch and Dash, they focused on using basically a dynamic confidence threshold. So instead of having the static threshold in the diagram I showed earlier for the probability distributions, it is basically making that dynamic, a moving state rather than static. And then DPSSL essentially generates the pseudo labels using data programming and different labeling functions. And so they were saying by combining both the consistency improvements in the consistency regularization and the improvements made in the pseudo label loss, they can essentially achieve a higher accuracy, which they haven't gotten to yet, but I'm sure will be released soon. And then to that point, this paper was released, I believe, in late May 22nd, I believe. But in comparison with this is for the CFAR 100 benchmark. It's actually second place right now compared to FixMatch with decoupled mix-up. And so I just thought was interesting because this one actually came out prior to this paper. So FixMatch plus decoupled mix-up came out, I believe, in March of this year. And so has a lower percentage of error, which I was confused about since it stated, DoubleMatch stated state-of-the-art error rates for CFAR 100. But yeah, I just thought that was interesting. So here are a few of the references. If you're interested, the link is in the Google Sheet. And that's it. So thank you, and I'll take any questions that anyone has.
Wonderful. Thanks for the fantastic presentation, Kyle.